Good morning, class. We are looking at section 2.1, starting with chapter 2, limits and derivatives, the tangent and velocity problem. So we are going to cover that section. We're going to go to limits of a function, calculating limits using the limit laws, the precise definition of limit, continuity, limits at infinity, derivatives and rates of change, derivatives as a function, okay? So, of course, this is a very short section. First, the concept of a tangent. The word tangent really means, the root of that comes from Latin, is tangens, which stands for touching. So there is a Euclidean definition, which says a tangent is a line that intersects the circle once and only once. And that is fine and dandy for something like that, but it may not work for all, shapes. So the line L intersects C only once, but it certainly doesn't look like what we think of as a tangent. What do we mean by that? Take a look at this one and take a look at this one, okay? If you look at the first one, obviously this is the Euclidean definition and it works for here, okay? But if you look at the definition that Euclid gives us, doesn't work for this one with the asterisk next to it, okay? Okay, so the line T, okay, is a tangent line, whereas the line L is not. So we want to distinguish between the two. And I really can't emphasize enough the importance of understanding how they really work out. So there is a line that crosses the graph at precisely one point, but that doesn't cut it. That's based on Euclidean definition, okay? On the other hand, there is a line that crosses the graph more than once, yet it is a tangent line at one of those points, okay? So that's what calculus will, tackle and answer accordingly, okay, class? All right, let's move on with the concept. Here's an example. Everybody's familiar with the basic function y equals x squared. And we are interested in finding the equation of a tangent line for this function for the graph of a function known as a parabola, okay? So how do we find an equation of a line? We need two things. We need the slope and we need a point. Now, we do have a point, but in order to find the slope, we need more information or we need 2 points and we don't have it. So the concept is what happens when you want to come up with the equation of a tangent line. How do you find the slope, okay? So we need 2 points, we don't have it, okay? So we can approximate it. How do we approximate it? We can pick up a point nearby, okay? To the right or to the left, it doesn't matter. And now that we have 2 points, we can calculate the slope. Now, the 2 points, when we connect them, the terminology, it's a secant. So we can calculate the slope of a secant line and, of course, the equation of a secant line. So the idea is that, of course, secant, again, it comes from Latin and it means cutting, okay? The idea is that we get closer and closer. So if I was to find this, okay, let's see what happens. So we choose a point that is not equal to 1, any point, okay? and then we calculate the slope. For example, if x is 1.5, so remember, x cannot be 1. So we pick something like, let's say, 1.5. And everybody remembers the definition of a slope, rise over run, change in y over change in x. We can calculate the slope of that secant line. Okay, so let's do that. When we pick up different numbers, notice we are trying to get to number 1. We will never get there. Take a look at this number. We are getting closer and closer to number 1, but we never get there. Because we never get there, we actually have 2 different points. One with x coordinate 1, one with x coordinate 1.01. But we are going to start far away. Number 2 is way far from 1. I want you to know that. And we calculate this. This is from one side. Let's do it from the other side. Now again, look at this number. So 1 starts from 2, okay? In other words, this is class, this is number 1. We come from the left and we come from the right of 1. And we get closer and closer to 1 on the x-axis, okay? So from number 2, we get close to number 1. From number 0, we get close to number 1. And as you can see, 1.001 and 0.999, they are extremely close. So if you look at the slope, let me use a different color here. The slope here, notice the trend and the slope for this last one. Notice the trend and the slope for the last one. There seems to be the slope is getting closer and closer to number 2. I hope you see that in a limiting band, okay? So we say the limit of the tangent line is the limit for the secant line as Q gets closer and closer to P. Remember, Q is a point on the graph. So take a look at the point Q. At the top here, that it's not at 1. It's just close and it's getting closer. So in this case, it's moving this way, okay? So according to this, there seems to be a number 2. Now, of course, y minus y1 equals m times x minus x of 1, and you can calculate the slope. It's really not a big deal. So as Q approaches P along the graph of this function y equals x squared, the graph is known as a parabola, we get to closer and closer to the slope of the tangent line. So take a look at these graphs. Q approaches P from the right. Q approaches P from the left. Okay. And that's the idea behind a tangent line. We try to get there from both sides. Now, if both answers agree, if you look at the left and right, you see the slope, one of them is 1.999 and one of them is 2.001. So they are approaching the same number, namely 2, then we say the limit exists, and that's the slope of this tangent. Okay. The velocity problem is the same. Okay, the ball is dropped from an observation deck 450 meters above the ground. We want to find the velocity after 5 seconds. And it follows the formula of S of t equals half of gt squared, or 4.9 t squared roughly. Okay, this is class, the formula S of t equals half of gt squared. It's really half of gt squared plus v0 t plus h sub 0. Let me add those also for the sake of those who are interested. For the complete formula, we also have plus v0, v sub 0 t plus h sub 0, and this is since this is a free fall, we don't have this. In any event, I want to erase that so I can give you room for, okay, well, we don't need it yet. All right, so as you can see, we are interested in finding the, velocity at a specific point. And remember, it's very simple. Total distance, okay, change in time, divided by total time change in distance over change in time. Okay, delta S over delta T. So with that being the case, okay, there's only a single time, okay. So what we are going to do, again, remembering that the definition of an average velocity, right? The distance over time. You can calculate this as S of 5.1 or minus S of 5 over 5.1 minus 5. And that gives us the V average as we go from 5 seconds to 5.1. Okay, so is this an instantaneous velocity? Is that the velocity at t equals 5? The answer is no. Okay, it's important to know. However, it's close. And so as we get closer, we get a better approximation. And that's the idea behind this. So take a look at this table, class. Notice what we are doing. Okay. First, look at the very first one. The distance is huge, okay? 5 to 6. Now we make the distance to number 5 closer and closer. We make it 5 to 5.1, 5 to 5.05, and we go down. And look at this one. This is even the closest. And as you look at the numbers in front, I hope you see the trend. The trend seems to be that these numbers are approaching a specific number, which seems to be 49. Okay? So according to this observation, okay, you would say the instantaneous velocity is 49 meters per second. This is a numerical approach, class. There is a graphical approach, numerical approach, and analytical or algebraic approach. This is the numerical approach to get us started. All right, class, good morning again. We are looking at the second section of the chapter. We are going to look at a limit of a function at the bottom. We do have, let me just do this and hide this. Here's the definition that we are going to look at the limit of f of x as x approaches a from the left, and the limit of f of x as a approaches from the right. And the limit exists if the two are identical. As we looked at the previous section, which was done numerically, we looked at the limit from both sides. All right, let's get started. So when we look at limits of a function, we have various methods. One of them is a numerical method. In essence, we have seen this. Basically, whatever limit you're interested in, you come from the right and left of that number. So if you're interested in finding the limit of f of x as x approaches a, then you find number a and you approach it from both sides, left and right. As you get closer and closer to a, you never get to a, by the way. X is approaching a, okay? If the y coordinate, which is really referring to the limit, they come together and they're the same, you say the limit exists, okay? So that's that. What else I want to look at is this definition. When the limit of f of x as x approaches a number, whether it's a, by the way, this one is called a from the left. A from the left, a from the right. So when we say a and we put a negative at top, it doesn't mean minus, it means a from the left. It is known as a one-sided limit. We're going to look at this, okay? And when we say a plus, that means a from the right. All right. If the result is infinity or negative infinity, that gives rise to the equation of a vertical asymptote. This is the summary of the section. I will look at every piece of it with more details. Now, what I want you to see is also the bottom part. This is the definition of a limit. The limit only exists if this part, which is limit from the right, and this part, which is the limit from the left, if they are identical, then the limit exists. All right, let's look at a graph that speaks volume, class. I want you to see all these graphs and understand what happens, and let's compare and contrast, okay? In all cases, the idea is that if we are looking at the concept of a limit, that means getting closer to A from the left and right. That's the concept of left side, arrow on the left of A, everybody, arrow on the left of A from the left, from the right. Now, as far as the limit is concerned, we are interested in finding values that we get close to A, but not at A. In all cases, okay, the limit exists. If you look at part A, this point, class, is f of A equals L. And the limit exists. If you look at part B, f of A is the y coordinate of this green point. And if you look at part C, f of A is undefined. So take a look at, and let's call that B. Take a look at this. Part A, f of A equals L. Part B, f of A is something else like B. Part C, f of A, we have no idea. It's not given to us. It's not defined. However, in all cases, the limit of f of x as x approaches A is L. If we understand this, we are done with the concept. So I'm going to repeat that. The idea behind the limit is not about what happens at A, but rather what happens in the vicinity of A, close by. So I want you to pay attention to these three graphs. In all cases, the limit exists. The first one, f of A equals L, which makes it a continuous function. In second case, f of A is not equal to L, which makes it a discontinuous function at x equals A. But f of A is defined as B. In part C, we don't even know what f of A is. So I hope it's clear. All right, we want to guesstimate the value of this limit class. We are interested in finding this limit, okay? So we want to look at this from the point of view of numerical, graphical, and then more importantly, analytical method. It is important to note that if you choose x to be equal to 1, the denominator becomes 0, okay? And therefore, the function is undefined at x equals 1, okay? The function is undefined at x equals 1. So why don't we look at cases where we approach 1 from both sides, okay? So we have number 1, we're gonna get close to it. So if on a number line, this is 1, from the left of 1, from the right of 1. So from the left of 1.5, 0.9, take a look. The numbers are getting closer and closer to 1 here. And look at the value of f of x. You do the same thing for the right. We are getting closer and closer to 1 again. So what do we notice? Take a look at f of x here and here. And if you have any doubts, you can even get closer. Add more 9s for x less than 1, add more zeros before the last one, okay? And from the table, I hope you see that the limit is 0.5 from the table, okay? From the table. And here's the graph. Take a look at the graph. Take a look at the graph. We are approaching 1 from the left and right. And as we do that, we get closer and closer to 0.5 from the top and the bottom. So we looked at numerical analysis, graphical, and now let's look at it from the point of view of analytical method, the algebraic method, which is a lot more important class, okay? Well, everybody knows how to deal with this expression. The denominator can be factored, okay? Let me use a different color here. So what is the limit? We factor, and the numerator ends up being only 1. And now we plug in 1. And this is how we are going to approach the algebraic approach class. We plug in and we observe. By the way, if you plug in at the very top, right here, if you just plug in, you get 0 over 0, and 0 over 0 is indeterminate. That means more work. I'm going to discuss that again before we start the analytical approach, the algebraic method, in a moment, okay? But for now, I hope you realize that we use the technique, algebraic technique, more specifically factoring to do the math, and it did work. So, numerical, graphical, algebraic method. We are mostly interested in algebraic method as far as the exam is concerned, mostly. All right. One-sided limit was put in the first page on the summary. So I want you to take a look at the bottom of the page and the definition of a one-sided limit. A function has a limit at a. The limit. The limit refers to the y-coordinate, okay, class? If the limit as x approaches a from the right, this is from the right, a from the right, when we say a plus, that means a from the right, is the same as limit as x approaches a from the left. So that's the definition. So let's look at this function h known as Heaviside function. H of t is equal to 0 if t is less than 0, and it's 1 if it's larger than or equal to 0. Okay, so you look at the limit as it approaches 0 from the left and then 0 from the right. When we say 0 from the left, we use the top function, h of t equals 0. 0 from the right, we use the bottom function because as t is larger than or equal to 0. And because they are not identical, the limit dne does not exist. dne, the limit doesn't exist. So symbolically, X approaches A from the right means that we consider only X which is larger than A. Okay, everyone? And of course, X approaches A from the left means that we consider X less than A. So I just wanted to sort of define, if you will, the concept of a one-sided limit. I hope everybody is comfortable with that. So one-sided limit, okay, uses the symbols A from the left, A from the right, and it follows accordingly. All right. I hope it's straightforward. We want to go to the next example, class. By the way, h of 0 equals 1. I want you to see why, because of the equality. That is the functional value. Later on, when we discuss continuity, this function is discontinuous at 0. But we say it's continuous at 0 from the right. We will look at that later. All right. Let's go to this example. We have a graph. Everybody can see it. And we are interested in finding the limit of this function. The function is called g of x. As x approaches 2 from the left, 2 from the right, and finally at 2. Okay. So think about the concept. 2 from the left. Class, 2 from the left. That means we are on this side of 2. And I hope you see when you look at the graph, that means we are going this way. We never get to 2. We are approaching 2. And therefore, we are approaching this hole, everybody. And this hole has a y coordinate, which is 3. When we are approaching 2 from the right, we're going this way. That means we are going this way. That means we are approaching this hole. And this hole, we never get there, but as far as the limit, we get there. The y coordinate for that one is 1. They are not identical. The limit does not exist. So I hope everybody is clear as to what's going on. Okay? The limit doesn't exist. Why? The limit from the left is 3. The limit from the right is 1. Okay? And they are not identical. By the way, you see both holes, class. So therefore, g of 2 is not defined either. So g of 2, we don't know what it is because both of them are holes and there is no solid point anywhere as long as the x coordinate 2 is concerned. Now we're going to do the same thing for number 5. We're going to approach number 5 from the left and right. I hope you see in the case of number 5, whether we come to the left, whether we approach from left or right makes no difference. In both cases, from the left and from the right, we are heading towards the same point, that hole which has y coordinate 2. Therefore, the limit exists and it is equal to 2. The limit of g of x as x approaches 5 equals 2. I hope it's clear to everybody. And what about g of 5? G of 5 is about 1.4. G of 5 refers to the y coordinate of this point, class. whatever you read, 1.4, 1.2, 1.5. The point being, they are not identical, okay, and that's why the function is discontinuous, but the limit does exist. The limit does exist. So with that being the case, let's go to the next example. Again, we want to make sure we can read this. This should be now nice and easy. It's a very easy read now. We want a limit of f of x as x approaches 2 from the left. That means we are interested, let me use a different color here. On the left side, that means we are in this branch. And so clearly we are heading towards the point, the solid point, which has y coordinate 3. And from the right, we are going this way. And that means we are heading towards the hole, which has a y coordinate 1. And therefore, the limit doesn't exist because the two are not identical, class. The two are not identical. Okay, it's very straightforward. Okay, we are repeating really the same question, if you will. And that's very straightforward. By the way, we'll discuss other things in a moment.
Professor?
Yes, go ahead.
Quick question. How did you get 3 for A, the limit of f of x, x is equal to 2 from the left side?
X is approaching 2. Okay, so if you look at the very first part, we are approaching 2 from the left. You know that 2 from the left, that means come to the left side of 2. You're okay with that, right?
Yes.
And which branch is this? This is the branch. If you look at the graph, there are 2 branches. So do you see this branch?
Yes.
So we are coming to 2 from the left, and we are ending up here having the y coordinate number 3.
Yes, I can see that.
Okay, sure. This one is number 3.
Thank you, Professor.
My pleasure. But from the right, we are coming to this point that has y coordinate 1. Does that make sense?
Yes,
Okay.
it makes sense. Thanks, Professor.
Perfect. Now, the next one is asking for f of 2. Now, what I want you to notice, when we are looking at a functional value, you have to have a solid point. Everybody can see the solid point here, class, solid point here. So f of 2 refers to this point. Let me actually do some cleaning here. F of 2. What is the y coordinate here? Okay, that's f of 2, which is 3. Then what is the limit of f of x as x approaches 4? Now look at number 4, the left side and the right side of 4. Here's the left side. Here's the right side. Whether we come from the left or right, we are approaching this hole, everybody. We are approaching this hole, which has a y coordinate 4. And then what is f of 4? There is no solid point. So what is f of 2 is 3. What is limit of f of x as x approaches 4 is 4. What is f of 4? I have no idea. It's not given to us. And by the way, you really don't want to say doesn't exist. It's undefined. However, as you do your homework or exam, the way they want you to answer, you answer it accordingly to get your 4 credit. So pay attention to the way you answer to your homework, then you do the same thing for the exam. I'm assuming we are okay with this class. All right. You really need to go back and look at this one more time, okay? I mentioned this definition, and I don't want to spend too much time on that. Everybody is familiar with vertical asymptotes, okay? And we've seen graph of vertical asymptotes in the case of rational functions. It has a specific definition. what happens when the limit goes to either infinity or negative infinity when x is approaching a number? It doesn't matter. In this case, a from the left, in this case, a from the right, in this case, from both sides. It doesn't matter. Is it infinity, negative infinity, makes no difference. We say it's a vertical asymptote. So with that being the case, I want you to see that this is the definition that I'm going to put up. The limit of f of x when x approaches a, whether it's infinity or negative infinity, or the limit of f of x, whether we approach a from the left or right, the vertical asymptote becomes x equals a. And as you know, in the case of y equals ln x, the VA is the y-axis or x equals 0. Notice the limit of ln x as x approaches 0 from the right is negative infinity. I hope you understand what that means, because it is extremely important that we be comfortable with graphs. Take a look at the graphs, take a look at your vertical asymptote. What it says, as x approaches 0 from the left, that one is undefined. We don't have a natural law, but only from the right, and it approaches a negative infinity. I hope you see that. It goes towards negative infinity. So having said that, let's see if we can figure out some of these questions quickly, okay? Take a look at the graph, okay? So having said that, the limit of r of x as x approaches 2, can you see when we approach 2, can you see that this goes down? And therefore this limit is equal to negative infinity class. Can you see that this is negative infinity? When we approach 5, okay, in both sides, this is approaching infinity, okay? In other words, those are the vertical asymptotes. So when we approach negative 3 from the left, we are here, class, okay? It's negative infinity, and from the right is positive infinity. I hope everybody can read this from the graph, okay? And therefore, we have the equation of a vertical asymptotes as x equals 2, 5, and negative 3. X equals to, not the numbers, x equals to, x equals 5, x equals negative 3 in any order you like. So the graph gives you what's going on, okay? Is there any question? Is everybody following what we just did? We are looking at limits and vertical asymptotes in this case, okay? Vertical asymptotes, okay, class? I hope it's straightforward. Okay, with that being the case, f of x equals tan x. Everybody remembers the graph. This is a basic graph from minus pi over 2 to pi over 2, if you remember, and we continue indefinitely on both sides. And the vertical asymptote happens basically when you have a denominator equal to 0 and tangent is sine over cosine. Okay. And cosine x is equal to 0. I hope you remember that in general, For example, cosine of pi over 2 is 0, or cosine of 3 pi over 2 is 0, or for that matter, negative pi over 2. So odd multiples of pi over 2, they result in cosine being negative, okay? So as an example, this is a function you are familiar with, okay? If you look at one, let's just do this. If you look at one cycle, only one, where x is pi over 2 here, and x is negative pi over 2. As you can see, okay, when we go towards pi over 2, okay, from the left, okay, and from the right, what happens? From the left of pi over 2, this tends positive infinity. In other words, so if this is pi over 2, on the left of pi over 2, we are going towards up here, positive infinity, okay? And from the right of negative pi over 2 happens the same thing, okay? And of course, you can expand that for more cycles. Pay attention to a complete cycle, okay? So for example, we can see from the graph and the green part that I put up, the limit of tan x as x approaches pi over 2 will depend is from the left side or the right side. If it's from the left side, it's positive infinity. But if it's from pi over 2 from the right, let me pick up a different color. What color can I pick here? Let's just pick this one. If we are on this side, everybody, that means really this part. Do you see that? If we are on the right side of pi over 2, then tangent is approaching negative infinity. So the bottom line is, what you really want to know is the following. The graph confirms that, is that the vertical asymptote, okay, are 2n plus 1 times pi over 2. 2n plus 1 represents an odd. So this means odd multiples of pi over 2. If you use odd multiples of pi over 2, okay, at those points cosine is 0, and those are your vertical asymptotes. On one side it goes to infinity, and on one side it goes to negative infinity. So I hope it's clear to everybody. Okay. Okay. This is a piecewise defined function, and we want to sketch the graph and then the limits and where it exists and so forth. So bottom line, when you have the graph, you can see what happens. Class, you basically look at each piece, okay, and you put them together. So for this one, you just graph sine x. Again, I'm reminding you what sine x is. Okay, this is sine x. This is the graph of y equals x. Okay, now 1 plus sine, the same thing is shifted up. Okay, the same thing is shifted up, class. So you can shift it up. And it's good for x less than 0. Remember, let me use a color just to make a point. This, I like to graph just a complete cycle, and then we can add to it more, okay, class? Okay, so a complete cycle and then add to it. And the way it has it, x is less than 0, it just has it on this side. And remember, whatever you see, you shift it up by 1 unit. So that's the sign. And what about the cosine? Here's the graph of cosine, class. Let me. This is one cycle, and you continue indefinitely. Now let's put them all together. For x less than 0, we get this portion. Because it has been shifted up and it continues, class, okay? It continues indefinitely. This is for x less than 0. Then we have a cosine, a portion of a cosine from 0 to pi. I hope everybody realizes that this is pi. So this is cosine. Okay, this is, let me give it numbers 1, 2, and 3. So this is number 1, this is number 2, this is number 3, and it continues indefinitely. Now, so what happens is that first, it's important to see that for the top part, class, look at this point. I want to make sure everybody understands what's happening. I want you to look at this point. Look at this point. First, we have a hole for the top part. Why is that? Because x less than 0, we don't have an equality. Then for the second part, you have the equality. Take a look at the second part, class, this part. It says x equals 0. At x equals 0, cosine is 1. So the whole becomes solid because of the second part. So they come together. Otherwise, they don't. Now let's look at the last part. What happens at x equals pi? At x equals pi, we are here for the second part, and therefore we are here. Take a look. Solid. But for the third part, it gives rise to a hole. Okay? It gives rise to a hole. And therefore, the limit exists everywhere, okay, except at pi, because the limit from the left and right are different. Okay? So the limit exists for everywhere except a equals pi. What is the limit? As x approaches pi from the left, class, take a look at pi. Let me use a different color here. Let's see what color maybe, okay, this one. As you come from the left of a pi, you're in this branch, so you have to write the y coordinate of this point, okay, class? Which is -1. From the right, you are moving towards this hole, so you have to write the y coordinate of this point, which is 0. And so you say limit from the left is -1. Limit of f of x as x approaches pi from the right is 0. Okay. And therefore the limit of f of x as x approaches pi does not exist. However, let me just do some cleaning here. Look at the fact this is solid. This is solid, everybody. Therefore, f of pi is given as -1. So I'm going to recap this. This is important that everybody follows. Okay. We have 3 pieces. The first piece is 1 plus sine x. Okay. So you graph sine x, you shift it up by 1, and you keep the portion on the left side of 0. Okay, class? So the graph that I had in the beginning, okay, you can lift it up by 1. And when you lift it up by 1, you do get this portion, if you will. And there is a hole here. Then the second portion is cosine x, and it fills up that hole, and it continues only up to pi. And then from pi, the function sine x takes over. I hope it's straightforward. All right, I want to look at it now from the point of view of algebraic process. So I'm going to tell you what we are going to do when it comes to limits. You basically plug in. So class, you plug in and you observe, okay? Then you plug in, what happens? Okay, let's write a few things. If you get to a number, you're done. If you get to a number over 0, you have to figure, well, let me put 0 over number first, I'm sorry. Let's just put it in an order that is more proper. 0 over a number. That is equal to 0 and you're done. If you get to number over 0, you have to figure out negative or positive infinity. Okay. However, most of the time we get to cases such as 0 over 0, infinity over infinity, infinity minus infinity, things of that nature which we call indeterminate. Okay, class? And I translate it into, what do we mean by indeterminate? I translate it into more work. We have to do more work, meaning we have to use our algebraic techniques to figure it out. So let's look at the very first one. I hope you see that if you plug in, you get 0 over 0, class. Plug in number 0, okay? You get square root of 4, which is 2, minus 2 is 0, and the bottom is 0. So when you get 0 over 0, there's a technique involved. For a case like this, you multiply by the conjugate, okay? Now, what is a conjugate? Recall A plus B. The conjugate is A minus B and vice versa. And their product is A squared minus B squared. So with that being the case, the technique is to multiply by the conjugate. When you multiply by the conjugate, each piece gets squared up. When you square the first piece, it simply comes out. Then minus, you square the second piece, you get 4, positive 4, and negative 4 cancel each other. And the numerator is only x. By the way, pay attention to the denominator. We don't distribute the x, we keep it. Why? Because we are actually hoping it cancels out. And I hope you see that x cancels out. The numerator becomes 1. The denominator is what is in the parentheses, nothing else. You plug in and you get 1, 4. So I want you to see that when we have 0 over 0, sky's the limit. We could end up with a number. We could end up with 0. We could end up with infinity. Who knows? You really have to work it out to figure it out. Okay, class? All right. Now, let's look at numbers 29 and 30 together. Both of them seem to be the same. We have the limit of x plus 2 over x plus 3. But in one case, x is approaching -3 from the right, one is approaching -3 from the left. First, I'm hoping everybody understands what we mean by -3 from the right and left, or any number from the right and left. It is important to put your number, in this case, the number is, and you can even pick up a test point from the left or from the right accordingly. Now, if you look at number 29, it says from the right of -3. So from the right of -3, this is for question number 29. Of course, as an example would be -2, but we want close, so we want -2.99999. I hope you realize that when you put -3 for the numerator, okay, it gives you -1, and because it's from the right or left, it really doesn't make much of a difference. It's important to see that the top is -1. Now -1.1 or -0.99 makes no difference. But in the denominator, the answer is 0. But why does it make a difference? Because 0 is the only number that on the left side is negative, on the right side is positive. I hope everybody understands what's happening. So I'm going to write something for both of them. I want you to see that. In both cases, we get -1 at top, 0 at the bottom. Okay? That's not a problem. In both cases, class, the numerator is close to -1. Now, whether it's -1.1 or -0.99, who cares? But the bottom that is 0 is not just regular 0. 0 depends how you approach it. So when you look at number 29, -3 from the right is like -2.9. Literally, if you replace this with like -2.9 and add it to 3, it gives you 0, but it gives you 0 from the right. Why is this important? When you divide a number by 0, you end up with infinity, okay, class? It's just that, is it negative or positive? The top is negative, the bottom is positive, so it's negative infinity. When you do the same thing for number 30, the top is -1. Now, what is this x, everybody? Let me use a different color here. Now, this x is -3 from the left, like -3, for example, 0.1. So the top is -1, but the bottom is like -0.1, the point being 0 from the left, everybody, 0 from the left. Why is this important? Because negative over negative is positive infinity. I hope you see the methodology I'm using here. If you use this methodology, it makes your life easy when you want to do the calculation. I hope you're paying attention. So one more time. When the denominator becomes 0, you have to figure out from the right or left, because it makes a difference between negative and positive infinity. Okay? Let's look at another example. Let's look at this case again, similar to the previous one. The denominator is 0. By the way, the top is class e to the power of 5, or e to the power of 4.9, or e to the power of 5.1, makes no difference. The top is a positive number. The bottom is approaching 0 to the third power. But is this 0 from the left or right? Remember, x is approaching 5 from the left. So literally, you can change that to, let's say, 4.9. As an example, I'm saying you can do it in your mind. So 4.9 minus 5 gives you negative. That's the point. I want you to see the sign. So we have e to the power of 5, and then 0 from the left to the third power. Now, as you know, negative to the power of odd is still negative. And therefore, we have positive over negative. negative infinity. Okay. Again, I want you to pay attention to this. Okay. Maybe I should, just. Let's look at the next one, class. When you plug in, you get 0 over 0. Always, it's a good practice to simplify a rational expression. When you do that, you can get rid of the x minus to everybody. So that's the first thing. Simplify your fraction if you can, your rational expression. You do the factoring, you simplify, it's not a big deal. Now, if we plug in, remember the top is 2, 1.9, 2.1. It really makes no difference. It is only 0 that you're concerned with. The denominator is 0. But is it 0 from the right or from the left? Can anybody tell me, is the 0 from the right or left here, and why? For this question, 0 from the right or 0 from the left for the bottom? Which one? Anybody?
From the left.
Beautiful. Because literally, replace the x. I mean that even in your mind or just literally. So 1.2 from the left means 1.9. 1.9 minus 2 means negative 0.1. So 0 from the left. Why is this important? The answer is not infinity. The answer is negative infinity, class. Okay? So I hope you see how you arrive at the answer. You have homeworks like that. And this is the fastest and easiest approach. And you can do this the same way for the exam. Okay? All right. The next one, cotangent X, and you may remember the graph class, that would be helpful, okay? Just for the sake of argument, if you remember the graph, this is the graph of y equals cotangent x, and this is x equals 0, and this is x equals pi. So if you remember the graph, when we approach pi from the left, the answer is negative infinity. Okay, so the graph of a function is really helpful. Or you can write it as cosine over sine. Okay, x is approaching pi from the left. Okay, now you have cosine of pi, and cosine of pi is negative 1. By the way, class, pi from the left and right of it, I want to make sure everybody understands. Think of pi as 180 degrees. So when we say pi from the left is like 179 degrees, okay, second quadrant. When we say pi from the right, like 181 degrees in the third quadrant. I hope everybody remembers the quadrants and so forth, right? Okay, quadrant 1. This is quadrant 2, quadrant 3, quadrant 4, and pi, class. Pi is right here. Okay, so when we say pi from the left, like 179 degrees, that means the second. In the second and third quadrant, both of them cosine is negative. The cosine is positive in the first and fourth quadrant. So that's negative 1. Okay, so but pi from the left, remember sine is positive in the first and second quadrant, and it's negative in the third and fourth. So if you want to approach it that way, you can say negative 1 over 0 from the right, and that gives you negative infinity. Whether you approach it this way or with the graph makes no difference. I hope it's straightforward. How about this one? ln of sine x, 0 from the right. You replace this with 0 from the right. And sine of 0 from the right is 0 from the right. This really is ln of 0 from the right. And you remember the graph. You can go back to vertical asymptote that was explained. And the graph is negative infinity class, okay? Negative infinity. So if you remember the graph, you can figure out what your answer is, okay? I hope everybody's clear on that. And finally, I want to go back to that first example we had and ask you, what if we had this one? So take a look at the first example on this page. What if the exponent instead of 3 was 4? And in other words, instead of odd, what if it were even? I hope you see that it becomes e to the power of 5 0 from the left to the fourth, and 0 from the left to the fourth is 0 from the right. And that's positive infinity, everybody. So I hope it's clear to everyone.